is right on the line.
We wipe it clean with the close the lid.
I think I'm just going to add captions to all these.
Set up. We're going to put the max wavelength, which we found was 605. We're going to go OK. We're going to click 0 because it's the best. So that's what we get. We can test it again, and our blank is still 0. So that's good. We've confirmed that the spectrometer is 0. So now we're going to open
It's popping up back in. Oh, so you do it. Okay. Is this great? What's in here?
Now that I've zeroed the photospectrometer with the blank, we'll see me visually scan the absorbance of the stock solution whilst I do a voiceover explaining why we would scan across all wavelengths, and I'll compare and contrast qualitative and quantitative data, and I'll explain all the variables in the Beer-Lambert law. We scan across all wavelengths of visible light to find lambda max. Lambda max is the wavelength of light that is most absorbed by the copper amine sample. For example, copper amine absorbed most at 605 nanometers, which we found because it is the highest peak in the scan application. We have quantitative data that the lambda max for copper amine is about 605 nanometers. The scans at 605 nanometers for different concentrations of copper amine solution will give us percentage absorbance data at different concentrations. Then we can plot an absorbance versus concentration graph. Percentage absorbance is a numerical quantity, but it is also relative to an arbitrary value that we designate to be 100% absorbance. In this way, percentage absorbance can be considered a qualitative value. This example shows how we obtained quantitative and qualitative data from the spectrophotometer. The equation for the Beer-Lambert law is absorbance equals E times L times C, where E is the extinction coefficient and it's specific to each species. For example, here it would be specific to copper amine solution. L is the length that light travels through the solution, and here, since the cuvette is 1 centimeter, length is 10 millimeters, and C is the concentration of the solution we are measuring the absorbativity of. So it would be 0.02 molar for the stock solution, and it would be more dilute from there for the serial dilutions that we did. We can measure the absorbance from the photospectrometer, and since we have all the other variables, we can rearrange the equation to calculate the value for the extinction coefficient. The extinction coefficient would also be the gradient of our absorbance concentration graph. If we fail to zero the machine, then other species than just copper amine will impact our absorbance value, and thus the absorbance value won't be the absorbance of pure copper amine, and thus it won't relate to the concentration of copper amine solution in each cuvette. Thanks for listening.